Identities are equations, but they are not any equations. They are equations that are true even when you substitute any values into the variables. So we have a lot of identities here, and because they involve the trigonometric functions, we are going to call this set of identities the trigonometric identities. We do need to memorize at least these two, although I'm going to put in the effort to memorize the rest of them. Okay, but for the rest of them, I have indicated an asterisk behind, which is to remind me that although I think it is a good idea to memorize them, but I can also find them inside the formula sheet. So let me show you where they are in the formula sheet. It is right here. Okay, so this entire set of identities here are going to be what I've indicated in the outline with the asterisk behind. And just to very quickly let you know how to read this identity, for example, when I see a sine square A, okay, this is pronounced as sine square A. So sine square A is interpreted as having sine A multiplied to sine A, so it is the same as sine A square. And let me just very quickly show you a numerical verification that these equations are true for all values of the variables. Let's pick one identity. Let's might as well just pick this, okay? Sine square A plus cosine square A is equal to 1. Is it always going to be true for any values of A? Let's try to make use of our calculator to do a quick verification. Let's pick a random value for A, okay? My calculator is now in the degrees mode. So let's pick an angle. Let's say we go for 37 degrees. Okay, let's see whether it is true that when we do a sine square what did I pick? 37 degrees. Okay, let's see whether it is true if we were to do a sine square 37 plus cosine square 37. Is it really going to be equal to 1? Let's try to press it into the calculator. So I'm going to press a sine square 37 degrees. So I have a sine, then 37 degrees, close bracket, and I'll square this. So this is the same as sine square 37 degrees. Then plus bracket, cosine 37 degrees, close bracket, square this. Is it really going to be equal to 1? Let's find out. Okay, it is equal to 1. We can also prove this identity. Let me try to show you how I can do that algebraically. I'm going to make use of a right-angled triangle. So on the right-angled triangle, this is 90 degrees. I'm going to call this angle here A. And this length here, I'm going to go for Y. This length, I'm going to go for X. And this length here, let's go for Z. Let's try to prove this first. Okay, then after that, I'm going to try to prove this. So if I were to prove this, I'm working on sine A, cosine A, and tangent A. Let's try to write down this tree based on the length on this right-angled triangle. So if we were to look at sine A is opposite over the hypotenuse. So it's going to be Y over Z. How about cosine A? Cosine A is the adjacent over the hypotenuse. So it's going to be X over Z. And as for tangent A, this is the opposite over the adjacent. So it's going to be Y over Z. Which means if we were to try to take sine A divided by cosine A, it is going to be equal to Y over Z divided by X over Z. And since these two X, Z can be cancelled, I'm going to be left with a Y over X. And what is Y over X? Y over X is tangent A. So tangent A is equal to sine A divided by cosine A. We have to memorize this. And because cotangent A is just simply 1 over tangent A, so it is also going to be 1 over sine A divided by cosine A, which is equal to cosine A over sine A. Let's try to prove this also by making use of the same right-angled triangle. We're going to look at what is sine square A plus cosine square A, and we are going to find out if this is really equal to 1. So sine square A is like sine square times sine square. It is like Y over Z times Y over Z. So we have a Y square over Z square plus cosine square A, which is X square over Z square. And since they share the same denominator, this we can rewrite it as Y square plus X square divided by Z square. But hey, what is Y square plus X square? According to a right-angled triangle that we are looking at here, Y square plus X square, using the Pythagoras theorem, it is Z square. So this is the same as Z square over Z square, which is equal to 1. That is why sine square A plus cosine square A is equal to 1 all the time. I can also make use of this that I've just shown. to try to prove the second identities that we have here, which is, I'm going to take this, okay, I'm going to divide this throughout by cosine square A. So dividing this by cosine square A, we have this over cosine square A. Then, of course, this, I'm also going to divide this by cosine square A, and this will be 1 over cosine square A. So what is sine square A over cosine square A? It is the same as sine A over cosine A square. And what is sine A over cosine A? It is equal to tangent A. So this is the same as tangent square A. Cosine square A divided by cosine square A, cancel, cancel, it is going to be equal to 1. And 1 over cosine square A is like 1 over cosine A square. And what is 1 over cosine A? It is secant A. Secant A square, this is going to give us a secant square A, which proves to us the second identity here. Let's just prove one more, okay? The last one. For the last one, I am going to take this and I am going to try to divide this throughout by sine square. So if I were to divide this throughout by sine square A, this divided by sine square A is sine square A divided by sine square A, and this divided by sine square A will be cosine square A divided by sine square A, and we have a 1 over sine square A on the right hand side. So this divided by this is 1. As for this divided by this is the same as cosine A divided by sine A, then the whole thing square. And cosine A divided by sine A is cotangent A. So this is cotangent square A. And this is like 1 over sine A, then the whole thing square. So we have a cosecant A, then the whole thing square, which means that this is equal to cosecant square A. And for the rest of the identities, we are just going to memorize them, and that we have done some manipulation to the identities that are going to be given to us in a formula sheet. I have these 2 green color ones. I think they are going to be very, very useful. It is just a simple manipulations from the original identities that are given to us. Let me just very quickly show you. For example, this double angle formula that we have here indicates that cosine 2A is equal to 2 cosine square A minus 1. Let me write it down here. So cosine 2A, this is equal to 2 cosine square A minus 1. So what if we need to express cosine square A in terms of, what if we want to express cosine A in terms of cosine 2A? So what we can do is to make cosine A the subject or cosine square A the subject, which means that I have 2 cosine square A. This is going to be equal to cosine 2A plus 1, which means that cosine square A, this is going to be equal to cosine 2A plus 1 divided by 2. So that is how I have derived this. And you can also try to equate this to 1 minus 2 sine square A. And manipulating this to make sine square A the subject, you're going to be getting this. And let me tell you one more thing about how we are going to be reading this list of identities. For example, this. Sine square, sorry, it's not sine square, this is sine. Sine A plus or minus B is equal to this. Okay, this plus or minus can be a little bit confusing. When you are trying to make use of this, you are definitely not going to write down the plus minus. So you are going to choose plus or minus. So for this, if I were to be using it, and let's say I'm going to go for a sine A plus B. Okay, so sine A plus B is going to be equal to sine A cosine B plus cosine A sine B. If I were to go for a cosine A plus B, then it is going to be cosine A cosine B minus sine A sine B. That is how I'm going to be interpreting this. And finally, if this were to be, if I'm going for a tangent A minus B, okay, I'm using the notation that is at the bottom, then you'll be tangent A, the bottom notation, tangent A minus tangent B, divided by 1, the bottom notation, 1 plus tangent A, tangent B. Let me show you some applications that we are going to be facing in our exams, that we are going to be applying identities from the list that we have here. So let me show you some examples and we're going to practice this together. Let's say solving equations. Okay, let's take a look at question number 1A. So in question number 1A, we are supposed to solve this. Cosine 2x plus cosine x plus 1, this is equal to 0, and we are given that x is between 0 radians and 2 pi radians. So in order for us to solve this, we are going to make use of the trigonometric identity list that we have. So let me refer back to this again. Let's see what we can use for the list that is given to us, okay? So how about re-expressing this so everything is in terms of cosine x, because now we have a cosine 2x and a cosine x. I don't think we can solve it in this way. So I'm going to make use of this here, double angle formula, to attempt to re-express a cosine 2x such that it can become a cosine x. And I'm going to make use of this. Cosine 2a is equal to 2 cosine square a minus 1. So this, I'm going to rewrite it as 2 cosine square x minus 1. Then plus cosine x plus 1, this is equal to 0. Okay, this, to become this, is me making use of this identity. Cosine 2a is equal to 2 cosine square a minus 1. Replacing a here by x. So now we have a 2 cosine square x plus cosine x. This is equal to 0. And now this equation is in terms of cosine x. I'm going to factorize out cosine x, which will give me a 2 cosine x plus 1. This is equal to 0. So cosine x is equal to 0, or 2 cosine x plus 1 is equal to 0. For cosine x is equal to 0, or for cosine x is equal to plus or minus 1, and even if it is sine x is equal to 0 or plus or minus 1, I mean, they are going to become like special angles, but I think a faster way for myself to be solving this is to just try to imagine it on this graph. So if I were to imagine this on the graph, if cosine x is equal to 0 or plus or minus 1, the graph, which I know the cosine x function is going to be like, is going to be something that is like this, from 0 all the way until 2 pi. And for cosine x to be equal to 0, it is here and here. And when will this happen? It is when x is equal to pi over 2, and this is when x is equal to pi over 3. This helps me to solve for this equation faster. So for this, based on me imagining the graph, I know x is going to be equal to pi over 2, or it's going to be equal to pi over 3. As for this, if I were to make cosine x the subject, cosine x is going to be equal to minus 1 over 2. So we're going to solve this equation by trying to imagine x on the 4 quadrants. Add sugar to coffee, ASTC. So cosine x is equal to a negative number. So in our imagination, we know that if cosine x is a negative number, it must be either in the 2nd quadrant or the 3rd quadrant. If it is in the 2nd quadrant, then it is going to be an angle that is like this. So this will represent x. If it is in the 3rd quadrant, then it is going to be something that is like this. This angle here is going to represent for us x. So the first thing that we want to do in terms of calculation is to calculate for the basic angle, which is this angle over here. So the basic angle, the reference angle, okay? So the reference angle, calculating this is going to be equal to, according to what we have discussed in the previous part, it's going to be cosine inverse of positive 1 over 2. And this will give us a special angle, pi over 3. Pi over 3 or 60 degrees, since we are dealing with radians, so we are going for a pi over 3. So now with this reference angle that is calculated, going for the 2nd quadrant, x is going to be equal to 180 degrees, but we are looking at radians. So 180 degrees is pi radians. So 180 degrees or pi radians, I will minus away the reference angle, it should give me this angle x. So this minus away pi over 3. As for this, I'm going to go for pi, which is this 180 degrees plus the reference angle plus pi over 3. So my answer here is going to be equal to 2 pi over 3 or 4 pi over 3. Let's take a look at the next one. Let's take a look at B. Let us see. Okay, we have this cosine square x plus 2 sine x is equal to minus 2. Let's try to solve this equation. So 1b, we are looking at cosine square x plus 2 sine x is minus 2, and this time we are working on degrees, where x is going to be between 0 degrees and 360 degrees. So now I have an equation and we have two trigonometric functions, sine and cosine, and that is not good. We should have just one single trigonometric function. So I'm going to go back to the list of identities that we have. And I think this time I'm going to pick this identity here. So for this identity, we see that it is sine square A plus cosine square A. This is equal to 1. And I'm going to try to re-express cosine square A and make it into the subject. It is going to be cosine square A is going to be equal to 1 minus sine square A. So this allows me to re-express cosine square x. And I can re-express cosine square x to become a 1 minus sine square x, making use of this, replacing the a by x. So I have this plus 2 sine x. This is equal to minus 2. And now I have an equation that is in terms of just sine x. Let's expand this equation and let's also bring everything over to the right hand side. So this, if I were to bring over to the right hand side, we have a sine square x. This bring over to the right hand side, we have a minus 2 sine x. 1, bringing over to the other side is going to be minus 1. So minus 2 minus 1, this is going to be equal to minus 3. And now we have an equation, a quadratic equation in terms of sine x. We're going to factorize this. Factorizing this in terms of sine x gives me a sine x minus 3 and a sine x plus 1. This is equal to 0. So which means that we have a sine x minus 3 is equal to 0, or a sine x plus 1 is equal to 0. For sine x minus 3 is equal to 0, that means sine x is going to be equal to 3, and this is not possible. According to what we have discussed in graph of sine x, we know sine x maximum is going to be 1, the minimum is going to be equal to minus 1. So sine x will always be between minus 1 and 1. It is impossible for us to get an x such that sine x is equal to 3. That is why we won't get a solution for this, but we will get a solution to this one here. And since sine x is either 0 plus or minus 1, just like what we did in the previous question, in question number 1a, we were using graph, okay, to find out what happens when cosine x was equal to, just now we were looking at cosine x was equal to 0. So I'm going to do the same thing for this. I'm going to just reference this to a graph. I think personally for me it is faster. So the graph is going to look something that is like this for a period that is from 0 degrees to 360 degrees, and we are working on minus 1. And when it is at minus 1, the angle is actually 270 here. So we know now that there's only one possible answer that's going to give us a minus 1 when x is between 0 to 360 degrees, and this x here is going to be equal to 270 degrees. Let's take a look at another question. Let's look at this one here. Let's look at C. In 1C, we are looking at 2 tangent x plus 2 cosine x is equal to 0. And x is between 0 radians and 6 radians. Okay, it's almost like between 0 to 2 pi, but 2 pi is 6 point something. So it is something that is slightly less than 2 pi. So now again, we don't have a good condition for the equation that is given because it is in terms of two trigonometric functions, tangent and cosine. So I'm going to try to convert all this into one single trigonometric functions. So I need to apply some identities first. Let's again refer to the list of identities that we have. And I think the first thing that I'm going to try to apply is going to be this here. So I'm going to re-express tangent to make it into a sine x divided by cosine x. So I have this plus 2 cosine x is equal to 0. And I think the next thing that I want to do is to multiply this throughout by cosine x, which will then give me a 2 sine x plus 2 cosine x times cosine x is cosine square x. This is equal to 0. Then I'm going to make use of this particular identity to re-express this cosine square so that it can be in terms of sine. So what is cosine square A? Cosine square A is 1 minus sine square A. So we have a 2 sine x plus 2, re-expressing this, it is 1 minus sine square x. This is equal to 0. So this I have a 2 sine x plus 2 minus 2 sine square x. This is equal to 0. Dividing throughout by 2 and bring everything over to the right hand side will give me a sine, it will give me a sine square x minus sine x plus, minus 1. Minus 1, this is equal to 0. So now I have a good and proper equation because it is in terms of just one single trigonometric identity, sine x. Sorry, one single trigonometric function, and that is sine x. So now we can solve this equation, this quadratic equation in terms of sine x by applying the quadratic formula. So sine x is going to be equal to minus b plus or minus square root of b squared minus 4ac divided by 2a. So sine x is equal to this, and if I were to just evaluate this, pressing into the calculator, I will be getting a negative 0.61803. So sine x is a negative number. We will be expecting sine x to be in the third quadrant, or it can be in the fourth quadrant. Again, ASTC, okay, I'm using that. So third quadrant, I'm looking at an angle x that is something that is like this. And if it is in the fourth quadrant, I'm looking at an angle x that is going to be something like this. So what we want to do next is to look at, is to try to calculate the reference angle here. So the reference angle will be sine inverse of positive 0.61803, and this, according to my calculator, is equal to 0.66623. So if x were to be in the third quadrant, then x is going to be equal to pi, which is equivalent to 180 degrees plus the reference angle. So pi plus 0.66623, or if it is in the fourth quadrant, then it is going to be 360 degrees, which is 2 pi. Then I will minus away this reference angle, 0.66623 radians. Let's see whether the x that we're going to be getting is between 0 to 6. So for this is equal to 3.81. Okay, it is acceptable. As for this, it is equal to 5.62. So these three questions that we have just done, they are equations, but there's also another kind of question which is going to become a very symbolic kind of question that is going to be tested for trigonometric identities. They will be making use of existing identities to prove more identities. So those questions will look like this. Let's try 2a. So in 2a, we are supposed to prove that this thing that is on the left-hand side is equal to this that is on the right-hand side. Okay, we are going to make use of the list of identities to prove these identities. And maybe good enough general rule that we can make use of when we want to try to prove identities is we are usually going to try to pick and start with the more complicated looking side. Okay, and the reason is because if it is more complicated, it is usually easier algebraically to simplify something that is more complicated than something that is already simplified and we want to make it more complicated. But it is not going to always work. So if you were to pick a side to try to prove the identity and you realize that it cannot work, then just pick the other side. So for example, in this 2a, I'm going to pick a side to start and manipulate it to make it look like the other side. So I'm going to start with the left-hand side, because I can tell that the left-hand side looks sort of like, definitely not sort of like, okay, it's definitely more complicated looking. So on the left-hand side, we are looking at a cotangent theta plus sine theta divided by 1 plus cosine theta. And let's try to see whether we can prove that this is equal to cosecant theta. And I'm going to make use of the list of identities that we have again. And I'm going to make use of this. Cotangent A is equal to cosine A divided by sine A. So I'm going to re-express this as cosine theta divided by sine theta. Then plus, this will be sine theta divided by 1 plus cosine theta. Let's think of a way so that we can manipulate this further and hopefully we are going to be getting a cosecant theta. So what I'm going to do is, how about combining this into one single fraction? So if I were to combine this into one single fraction, then it will be cosine theta 1 plus cosine theta, then plus sine theta times sine theta. It is going to give me a sine square theta. This is going to be divided by sine theta 1 plus cosine theta. So we have a cosine theta plus cosine square theta plus sine square theta. This is divided by 1 plus cosine theta. Hey, what is this? Cosine square theta plus sine square theta, according to this identity over here, it is equal to 1. That is why for what we have here, oops, I've forgotten this. It is sine theta multiplied by 1 plus cosine theta. So if we were to simplify this by making use of the existing identity that we have, then this is going to be plus 1. So we have this divided by sine theta, then 1 plus cosine theta, and these two, they are the same. So I can actually cancel them away and I'll be getting a 1 over sine theta. And what is 1 over sine theta? This is cosecant theta, and this is equal to the right hand side, which is what I'm supposed to be proving in part A. So this is now proven. Let's take a look at question number 1b. 1b is this. Okay, let's try this. Sorry, 2b. So 2b, okay, not 1b, it is 2b. 2b, this is, okay, I'm supposed to prove this, okay, I'm going to pick one side to try to start. So one side is secant 2 theta, which looks pretty okay, simple enough. So I'm going to pick the more complicated looking side, which is actually the right hand side. So let's try to see whether we can achieve our identity, proving our identity by starting with the right hand side. Right hand side is 1 plus tangent square theta divided by 1 minus tangent square theta. And okay, we're going to make use of identities to prove identities, okay? So I'm going to make use of this first identity here to replace tangent square theta. So it will be 1 plus tangent theta is like sine theta divided by cosine theta. So square of this is like sine square divided by cosine square. So it's the same thing for this. This is 1 minus, this will be sine square theta divided by cosine square theta. And I think what I'm going to do next is I'm going to try to combine the numerator into one single fraction, which will be cosine square theta plus sine square theta divided by cosine square theta. This is the numerator. I'm going to do the same thing for the denominator. It is equal to cosine square theta minus sine square theta divided by cosine square theta. So the denominator actually can be cancelled away, and I'm going to be left with this, which is cosine square theta plus sine square theta, that is equal to 1. So for the numerator, I'm going to be left with a 1 divided by the denominator, which is cosine square theta minus sine square theta. Do you find this familiar? Because I do. I've seen this somewhere, and it is under this double angle formula, specifically this. Cosine 2a is equal to cosine square a minus sine square a. And we have a cosine square theta minus sine square theta, which means that this here is going to become a cosine 2 theta. And what is 1 over cosine 2 theta? This is secant 2 theta, and this is equal to the left hand side. And now we have managed to prove this identity. Let's take a look at 2c. In 2c, we have this, okay, involves tangent. So 2c, we need to pick a side to start. Okay, which side should we prove? Because both left and right hand side, they actually look pretty okay. So based on my experience, okay, because if it doesn't work, I'm going to just pick the other side. It is fine. I'm going to try to start with the right hand side. So if I were to start with the right hand side, that means I'm going to be working on a sine of a plus b divided by sine of a minus b. let me go back to the list of identities that we have here, and I guess it is pretty obvious that I'm going to be using the addition formulas. So for the numerator, if I were to make use of this, sine A plus B is going to be written as sine A cosine B plus cosine A sine B divided by sine A minus B. So I'm using the symbol that is at the bottom. So I'm going to synchronize that for here also. So the denominator will be sine A cosine B minus cosine A sine B. And what I'm going to do next is I am going to try to divide throughout by both the numerator and the denominator. Okay, I'm going to divide both the numerator and the denominator by cos A cos B, cosine A cosine B. So for the numerator, sine A cosine B plus cosine A sine B. I'm going to divide this by cosine A cosine B. Since I did this in the numerator, I'm going to do the same thing for the denominator. So for the denominator, we have this minus cosine A sine B. I will also divide it by cosine A cosine B. Why are we doing this? Because if I were to take this divided by this, then the cosine and cosine will disappear, which means that I'm going to be left with a sine A divided by cosine A. And what is sine A divided by cosine A? It is tangent, right? It is here. It is tangent A. So this will become tangent, and this sort of like synchronized to what we have, what we are given on the left-hand side. It is a tangent A. As for this divided by this, cosine A and cosine A can be cancelled. I'm going to be left with a sine B over cosine B, which in the next step, I'm going to rewrite this as tangent B. So for this, cosine B and cosine B can be cancelled. I'm going to be left with a sine A divided by cosine A minus, for this, cosine A and cosine A can be cancelled. I'm going to be left with a sine B over cosine B. So this is tangent A, and for this is going to be tangent B divided by this is equal to tangent A, and minus this, which is equal to tangent B, and this is equal to the left-hand side. And henceforth, we have proven part C. Let's look at the last one, D. In D, we have this to prove. So 2D, I think I'm going to go for the left-hand side. Okay, so if I were to go for the left-hand side, that means I'm going to be working on a tangent A minus pi over 4. And the identities that I'm going to be using, one of them will be this over here. Addition formulas, tangent A plus B, or tangent A minus B, which we have a case here. So we are using minus, which is the symbol that is at the bottom. So I'm going to use the same symbol that is at the bottom for all this that is on the right-hand side. So re-expressing this is going to be equal to tangent A, according to what we have in the identity list, it is going to be minus tangent pi over 4 divided by 1, and this will be plus. Then tangent A, tangent pi over 4. Pi over 4 is a special angle. So what is tangent pi over 4? We can press it into the calculator, or if you have already memorized this, tangent pi over 4 is equal to 1. So we're going to be left with a tangent A minus 1 divided by 1 plus tangent A times 1, which is going to be just tangent A. So we're going to prove that this can be equal to something that involves sine and cosine. So I guess it is obvious that the next identity that we are going to be making use of is this one here. So this is equal to sine A over cosine A minus 1 plus divided by 1 plus this is going to be sine A over cosine A. And I'm going to make this into one single fraction because we already have similar experience in the previous part. So making this into one single fraction, we will have a sine A minus cosine A divided by cosine A. And I'm going to do the same thing for this. It is going to be cosine A plus sine A divided by cosine A. So the denominator can be cancelled for both this and this. And what I'm going to be left with is going to be this sine A minus cosine A divided by this, which I'm going to write this as the first term. So it's going to be sine A, then this, plus cosine A. And this is the same as the right-hand side. Do make sure that you spend a lot of time doing a lot of practice for trigonometric identities, especially proving identities. I think the more that you try such questions, the better you will become. And once you are good enough, let's move on to the next part of the chapter. And I'm going to just see you there, okay? It is called the R formula.